Hey everyone, hope you're doing well. Today's video is going to be on the pumping lemma for regular languages. So, before we get started on the pumping lemma, let's focus on some prerequisites because I think understanding these two theorems here will really help us understand the pumping lemma a lot easier. So the first theorem is Kleene theorem. And the second theorem that's a prerequisite is the directed circuits theorem. I'm not sure exactly what the name of it is, but you will understand it when we go through this. So first, Kleine's theorem. Kleine's theorem states that all regular languages can be expressed as a regular expression, a finite automata, a non-finite automata, or a generalized non-finite automata. So essentially, whenever we have a regular language, we can say that there exists one of each of these types, something of each of these types that represent that regular language. This will come in handy in the pumping lemma as well. And the second one is the more complex theorem, because as you know, Kleine's theorem is a fundamental theorem that you've probably seen so many times. But the directed circuits theorem is something a little bit more complicated, that is more advanced and also more crucial for understanding the pumping lemma. But before we look into the theorem, let's understand what a circuit is. A circuit is a path in a finite automata that starts and ends at the same state, not start state, at the same state. So let's take a look at a cycle in here. So for example, if I'm at state 1 and I process B, then A, I come back to state 1 again. That's a cycle, right? So it's a path within a finite automata that starts and ends at the same state. There's other cycles as well. For example, if I start at 1, I go B, right? And then I come back to A. That is also a cycle. So hopefully the idea of a cycle makes sense now. So essentially what this theorem says now is that in a finite automata with n states, the path taken to process a string S that has greater than or equal to n characters always contains a cycle. Right? Let's take a look at an example here and see if this is true for an example. That doesn't mean the theorem holds, but it's good to just test it out with some examples. So let's take a string to process. Let's say A, B, A, B, A, A. Okay, this is a string of length 1, 2, 3, 4, 5, 6. So it's 6, which is bigger than the number of states, which is 4. Therefore, by this theorem, there should be a cycle. So let's process this string. So we start at state 0, right? Then we go from 0, we process A, and we go to 1. Then we process B, and then we go to 2. Right? We started here, here. Then we process A, and we go to 1. Oop, already a cycle, so that's good. And then we process. So we've done A, B, A to get to 1, and then B again to get to 2, and then A again to get to 1. There's 2 cycles, actually. And then finally, the last A will take us to 1 again. So a lot of cycles in this path. So there's clearly a cycle there, but let's take a look at another example. Maybe let's do something with just exactly 4 characters. So let's do A, B, B, A. Okay, A, B, B, A. Again, we start at 0, right? And then we process A. to get to 1. Then we process B to get to 2. Then we process B again. And this time we get to 3. And now we process A. Where do we end up at? 3. You pull the A path, gets back to 1. So again, now this one's less obvious, but the cycle here is when we start from 1, go B, B, A. Or we can look at here, it's literally just as soon as this 1 repeats, we know there's been a cycle. So I think there's a key observation I want you to make from this example that will help us in the proof. And that observation is that a cycle occurs whenever a state repeats itself. Right? For example, the cycle appeared as soon as 1 repeated itself for the first time. Same here. The first cycle came about when processing A, B, A, B, A, A, when we came back to 1 for the second time. So as soon as you revisit a state you've already visited, you form a cycle because there was a path from the state from the state originally to now. So this is going to be the key idea for the proofs. So now we'll use some word explanation to show that a path taken to process a string S with S greater than or equal to n always contains a cycle. So that's going to be the idea for this proof. All of this entire paragraph is that we will revisit some state once at least. So I'm going to use the opposite. So if a circuit occurs when there's if a circuit occurs when there's a repeated state, I'm going to assume that we can process S with a path that does not contain a cycle, right? And that also means that there's no cycle, that since there's no cycle within this path, that there are no repeated states. So that means each state is visited at most once. Does that make sense? So we assumed, we saw that a cycle occurs when a state is visited for the second time. So if there's no cycles, that means that each state is visited at most once. We also know that the maximum number of states that can be visited is equal to n. And further, since we know that each character corresponds to visiting a new state, right? Each character corresponds to visiting a new state. The maximum number of characters that can be processed is 1 less than the number of states, or n minus 1. The reason it's n minus 1 and not n is because the start state, we're at there after we've processed 0 strings. So when we've processed 1 character, we've been to 2 states. So it's always 1 more state than there are characters. So when there's n states, there's n minus 1 characters that can be processed at most. But this means that if there's n minus 1 characters, it also means that S is less than n. But this directly contradicts the condition that S is longer than the number of states. Therefore, our initial assumption must be false, and therefore we cannot process S with a path that does not contain cycles. Okay, so that's the directed circuits theorem. This is very, very important for the pumping lemma. So now we'll get to the pumping lemma and we'll see how all of this comes together. So, suppose the key condition for a pumping lemma is that it only applies to infinite regular languages. And the pumping lemma basically says that since it's a regular language, we know that, let's call it R, has a finite automaton. And since it has a fixed number of states, let's say it has n states. And it basically says if we choose a word from the regular language such that the word has length bigger than or equal to n. By the way, sorry, if you choose any word, I think we need to emphasize that. Any word from R that has length bigger than or equal to n, then the pumping lemma states that W contains a substring x, y, and z that satisfy the following properties. W is equal to x, y, z. Sorry, I should emphasize y is not equal to empty string. So let me reiterate. The pumping lemma states that W contains a substring x, y, and z. And I think that's an extra condition on y, but it's not the empty string, that satisfy the following property. W is equal to x, y, z. The length of the first part, x, y, is less than or equal to n. And x, y to the power of I, z belongs to R for every single I greater than or equal to 0. So there was a lot of word vomit, but let's try to understand this visually. So essentially, what's happening is this. Now there's suppose, this is the finite automaton of the regular language we care about. It's a very simple one, but the idea will generalize to any finite automaton. So we know this has 4 states. So if you pick any word in this language that has more than 4 letters, I'm going to pick one quickly. Let's say A, B, B, A, B, B. Right? So this is a word that belongs to the language. You can actually see if you process the string, it will end up at state 3, which is the accept state. So if we start here, 0, we go to A, B, B, A, B, B. We're in the accept state. So this word does belong to this language. And what it basically says is we can split this word W, let's call it W, into 3 parts, into X, Y, and Z. And we're going to choose the X, Y, and the Z carefully. We're going to choose the Y to be something particular, which is the loop. The loop here is B, B, A. So I'm going to call this the Y. Right? That means this must be the Z and this is the X. And it's basically saying, if I just repeat this Y section, no matter how many times I repeat this Y section, I will end up with a word that belongs to this language. Right, so if I have anything of this form, it will belong to this language, is what this theorem says. Is that true though? Because I'm just focusing on this condition. X, y to the power of I, z is an element of R for all I bigger than or equal to 0. Why would that be true? Well, let's see here. What if you repeat BBA twice? Right, so the word would be A, BBA, BBA, BB. A, A, B, B, A, B, B, A, B, B. Oh, it's still accepted. Okay, that makes sense, but that doesn't prove it for all states. So we need to have some sort of argument that it will work for all values of I, right? No matter how many times we repeat Y, it will still belong to this language. And that comes from the fact that this is a cycle. We're repeating a cycle, right? We have A, B, B as a word, but A, B, B, A, this first cycle, we come back to the same state, and we go B, B. No matter how many times we cycle this, we will always come back to the first state, and we'll go from there to the end to reach the accept state. So when we go A, B, B, A, we end up at 1 before we do the last two strings. We're at state 1 here. And then if we go A, B, B, A, B, B, A, we're still at state 1 before the last two strings. So no matter how many times we repeat this, because it's a cycle, we come back to this state 1. Therefore, we can just pump it. That's where sort of like, it's called the pumping lemma. We're pumping this Y. Just pump it, pump it, pump it, pump it, right? Just repeat it forever. And that's basically the visual idea behind the pumping lemma. And this works because of the directed circuits theorem. Because as long as we pick a word of length greater than or n, there will be a cycle. And since there is a cycle, we just need to choose y, let y be the cycle, and we can just pump it forever. So that is the key idea behind this pumping lemma. Right, so we can pump it forever because of that. And now we can revisit this, right? So let's understand why we do each of these steps now. We choose a finite automaton to represent the language. So let's focus on this first step. Why do we focus on the finite automaton? Well, we use the finite automaton because we want to use the property that there will be a cycle or a directed circuit within this finite automaton. And then because we chose a finite automaton, the theorem, we need to use a word that is has sufficient length, right? We need the word to be at least of length n to have we need the word to have at least length n to have a directed circuit guaranteed in it. And then it says it contains a substring. It doesn't mean all substrings. It just means one of these break, like, not all, like, we could, let's say we have a word. We could break it down in a lot of ways, right? A, B, A, B, A. We could also break it down A, B, A, B, A. Something like that. But what it's saying is, not all of them, but there's always at least one breakdown of W into X, Y, and Z, such that W is equal to X, Y, Z. The first part is less than or equal to N. And then X, Y to the power of I, Z is an element of R. This is the pumping. This, you can pump it forever because you've chosen a directed circuit for Y. And in predicate logic, what it says is, for all W, there exists X, Y, and Z, such that for all I bigger than or equal to 0, W being bigger than or equal to N implies these three conditions that we saw here. And so that's basically an explanation of that now. Now, I guess something I didn't go over was why xy not greater than, xy less than or equal to n is a condition. Right? Why is it that xy is less than or equal to n a condition? Well, this condition isn't compulsory, but it just makes the argument stronger, and it will make the proofs a lot easier when you do it. But the reason this extra condition is also true is because as soon as you've hit n letters, you've always hit you always hit a state that you visited before. Because remember, if there's n letters, that means you visited n plus 1 states. Right? N letters implies n plus 1 states. This is one of the arguments we made in the proof for the directed circuits theorem. And if we're at n plus 1 states visited, that means we must have visited a state we've been to before, because we know there's only n states in total. And as soon as we visited that n plus 1 state, we are guaranteed to have had a directed circuit. So that's why this is extra condition that exists. Okay, so that is the fundamental idea of the pumping lemma. And the thing is, the pumping lemma is very positive in nature. What that means is that the pumping lemma is a property of regular languages. But actually, its application is negative. And what I mean by that is, we actually don't use it for regular languages. We use it to prove that a language is not regular. And we'll go over this in the next video. But that's it for this video, and hopefully the pumping lemma now makes sense. But this application is very important, and we will cover that as well. Thank you. Bye.